MITP for both MITP staff for the support and also for this wonderful initiative of young stars for giving us the opportunity of giving this workshop. And so there will be, as Ricardo said yesterday, there will be 2 talks per day. Each talk will last 55 minutes, more or less, with 5 minutes for questions. And between the first and the second talk, we will have a short break. After the second talk, we will have a slightly longer break, and then a discussion session, a 1-hour discussion session. And today we start with Evelyn Rodriguez. So I thank a lot to the speakers also for having accepted our invitation, and it is an honor to have all of them here together. And also all the participants, thank you very much for being here. And I'm very glad to introduce my colleague and friend, Evelyn Rodriguez, who will talk about the Chern-Simons Supergravity theories with torsion and their non-relativistic limit. So Evelyn, please, you can share your screen, and the ground is yours.
Thank you, Lucrezia.
Thank you.
I will share it. Okay. I'm sorry, I will change this. C'è un casino. Can you see my screen now?
Yes, perfect.
Yes, I'm sorry. Okay. First of all, I would like to thank the organizers for the invitation and for the opportunity of sharing with you part of my recent work. I will turn off this. Okay. Today, I will talk about 3-dimensional Chern-Simons Supergravity theories with torsion and non-relativistic limit. The talk is mainly based on these 3 works. The first one was a collaboration with Hamed Adami, Patrick Concha, and Hamid Safari. The second one was the result of a collaboration with Ricardo Caroca, Diego Molina, and Patrick Concha. And the last one, which is the more recent, it appears just today on arXiv, was the result of a collaboration with Patrick Concha and Lucrezia Ravera. The outline of the talk is the following. First, I will give a very brief introduction to the so-called teleparallel gravity theory. Then, using the Chern-Simons formulation, I will show you how to construct this theory, and also the corresponding supersymmetric extension. Then I will consider the non-relativistic counterpart of these theories. And finally, I will show a Maxwellian generalization of gravity with torsion. Well, teleparallel gravity is an alternative theory of gravity known to be considered equivalent to general relativity. However, they are conceptually quite different. In particular, the teleparallel formulation of gravity is described by a vanishing curvature and non-vanishing torsion. Then we have, instead of having a Riemannian geometry, we have which is called the Riemannian-Cartan geometry. 3-dimensional gravity with torsion possesses a BTZ-like black hole, which was denoted as the teleparallel black hole. And the asymptotic symmetry is described by 2 copies of the Virasoro algebra So GR with cosmological constant and teleparallel gravity in 3 dimensions have identical asymptotic structures. Teleparallel gravity can be derived as a particular case of the topological gravity model proposed by Mielke and Beckler, whose action is given by this expression, where A, lambda, beta 3, and beta 4 are free parameters, and where the first term is the Einstein-Hilbert term. The term along lambda is a cosmological constant term. Beta 3 yields the gravitational Chern-Simons term, and the last one along beta 4 is the torsional Chern-Simons term. Here R is the curvature to form, the Lorentz curvature to form, and T is the usual torsion to form. For the particular choice of these free parameters, we can regard, for example, Einstein-Hilbert gravity, teleparallel gravity, or the exotic Witten's gravity. In particular, the 3-dimensional teleparallel gravity can be derived by fixing the parameters A, lambda, and beta 4, which appear in the Mielke-Beckler gravity in this way, where G is the gravitational constant and L is a length parameter related to the cosmological constant. With this choice, the Mielke-Beckler action takes this form, where we have defined this beta 3 tilde in this way. And this is the action for the teleparallel gravity. And as we will see later, the equation of motion coming from this action are those describing a non-Riemannian geometry, which is a curvature, a vanishing curvature, and non-vanishing torsion. Well, we have shown that this gravity action can be also obtained as a Chern-Simons gravity action invariant under a particular deformation of the Poincare algebra, which is spanned by the rotations J and the generator of translations P, which satisfy the following commutation relations, and where we fixed the deformation parameter as -2 over L, where this is L is related to the cosmological constant. We have denoted this algebra as a teleparallel algebra. We can see that when in the flat limit, so when L goes to infinity, this algebra reduces to the Poincare one. It is possible to show that when we consider this redefinition of the generators, the teleparallel algebra can be written as 2 copies of the Lorentz algebra in 3 dimensions. Let us move on now to the construction of the Chern-Simons action. For this, we will consider the gauge field connection one form A for the teleparallel algebra, which reads in this way, where the field along J is the spin connection, and this is the field line. And the corresponding curvature to form F is given by this, where the components are the usual Lorentz curvature, and T hat is given in terms of the usual torsion to form. The teleparallel algebra also admits the following non-vanishing components of an invariant tensor, where alpha 0 and alpha 1 are arbitrary constants, which are related to the Lorentz constant through these 2 expressions. So if we consider these components of the invariant tensor and the gauge potential one form in the general definition of the Chern-Simons action, we obtain this action, which, as we can see, coincides with the teleparallel action obtained by fixing the Milky-Baker parameters when we identify alpha 0 with beta 3 tilde and when alpha 1 is 1. Here we see that the first term is the gravitational Chern-Simons term, and the term along alpha 1 contains the usual Einstein-Hilbert-Lagrangian, a cosmological constant term, and a torsional Chern-Simons term. Let us note also that when L goes to infinity, we recover the action for the Poincare. Now, by varying the action with respect to the field content, we obtain this equation of motion, and imposing these two conditions, which are necessary to have a non-degenerate invariant tensor. These equations can be written as the vanishing of the curvature to forms. Then we obtain the vanishing of the curvature, the Lorentz curvature, and we obtain a non-vanishing torsion. We can see that here the cosmological constant can be seen as a source for the torsion. These field equations are geometrically dual to the ADS ones, which are characterized by a Riemannian spacetime. But here, this teleparallel gravity describes a non-Riemannian geometry with the vanishing curvature and a non-vanishing torsion. Well, we have also considered the supersymmetric extension of the teleparallel gravity theory. For doing so, we have first considered the supersymmetric extension of the teleparallel algebra. We have denoted this superalgebra as the teleparallel superalgebra, which is spanned by the generators J, P, and by the fermionic charges Q, which satisfy these commutation and anti-commutation relations. Here we can see that when we consider the flat limit, this superalgebra reduces to the Poincare superalgebra. The teleparallel superalgebra can be written as the OSP21 cross SP2 superalgebra by considering this identification of the generators, where L and J satisfy the OSP21 superalgebra, while S is the SP2 generator and satisfy this algebra, superalgebra. But although this superalgebra is isomorphic to the OSP21 cross SP21, we will see that they have differences, for example, at the dynamics and geometric level. Let us consider now the construction of the supergravity, Chern-Simons supergravity action invariant under this teleparallel superalgebra. For this, we consider the gauge field connection one form for the teleparallel superalgebra, which is given by this expression, where this is the spin connection, the field line, and the Majorana fermionic one form describing the gravitino. And the corresponding curvature to form is given by this, where these are the components. And in particular, Nabla psi defines the covariant derivative of the gravitino. Here we can see that unlike the ADS or the super ADS case, the field line doesn't contribute to the covariant derivative of the gravitino. Well, the teleparallel superalgebra admits the following non-vanishing components of a non-degenerate invariant tensor. And when we consider this component and the connection one form in the general form of Chern-Simons action, the action we invariant under the teleparallel superalgebra is given by this action. This can be seen as a teleparallel supergravity action invariant under the teleparallel superalgebra, and it contains two sectors proportional to alpha 0 and alpha 1. In particular, the term along the alpha 0 corresponds to a supersymmetric extension of the gravitational Chern-Simons term or exotic action. Unlike the ADS supergravity action, the exotic term does not contain a torsional term, but it appears along the alpha 1 constant with the Einstein-Hilbert term, a cosmological constant term, and the fermionic kinetic term. And here also, if we consider the flat limit here, we recover the action for the Poincaré superalgebra, where the exotic sector is no longer supersymmetric. Now, the field equations coming from the previous action are given by this. But again, if we consider the non-degeneracy of the invariant tensors, which require these two conditions on the arbitrary constant, we see that this can be written as the vanishing of the curvature to forms. Well, this theory then corresponds to a supersymmetric extension of the teleparallel gravity, being characterized by a non-vanishing super torsion. Well, this result could serve as a starting point for different studies. For example, we could analyze the boundary dynamics, for which we would expect to obtain a superconformal structure. It would be also interesting to explore the non-relativistic counterpart of the teleparallel supergravity theory, and this to elucidate the role of torsion in a non-relativistic environment. And also, we could explore Maxwellian generalization of the teleparallel gravity. We have already approached these last 2 points, and now I will tell you about the result we have found. Well, non-relativistic theories have received a growing interest due to their relation to condensed matter systems and non-relativistic effective field theories. Non-relativistic theory can be obtained by considering a suitable limiting process from a relativistic theory. In particular, in this talk, this limit corresponds to the limit in which the speed of light tends to infinity. Well, at the gravity level, it is well known that the symmetries, the non-relativistic limit of the symmetries of ADS spacetimes correspond to the so-called Newton-Hooke symmetries, whose flat limit leads to the ordinary Galilei symmetry, being this the non-relativistic limit of the Poincaré algebra. In the limiting process, there might appear infinities in the expansion of the original Lagrangian, and in order to overcome this difficulty, a possibility is consider an enlargement of the field content. As we will see later, the presence of these extra fields are crucial in order to get a finite Lagrangian, and also in a Chern-Simons formulation, they are important in order to get a non-degenerate invariant tensor, which is a key ingredient in the construction of a Chern-Simons action. For example, in the case of Poincaré, the non-relativistic limit of the Poincaré, as we saw, is the Galilei symmetry. When we consider an enlargement of Poincaré with one U1 generator, the corresponding non-relativistic limit is the Barman algebra. But if in 3 dimensions, we can consider another another enlargement in order to have a non-degenerate invariant tensor, and the corresponding non-relativistic limit is an extension of the Barman symmetry. In the case of the ADA symmetry, an enlargement with 2 U1 generators, the corresponding non-relativistic limit is the extended Newton-Hooke symmetry. Motivated by this result, we studied the non-relativistic limit of the teleparallel algebra. For doing so, we considered an enlargement of this algebra with 2 U1 generators, since we knew that the flat limit of the teleparallel algebra corresponds to Poincaré. And well, as I said before, a torsional non-relativistic algebra can be obtained by applying the non-relativistic limit to a particular U1 enlargement of the teleparallel algebra. For this, we introduced 2 extra U1 gauge fields to the field content. So we have here I changed the notation for convenience, because I have to decompose this capital index for doing the non-relativistic limit, but this is the spin connection, this is the field line, and the M and S are the extra field, are U1 gauge fields. And these extra generators yield the following non-vanishing invariant tensors. So we have for the teleparallel algebra, we have enlarged with these U1 generators, we have non-vanishing components, these 3 plus those for the teleparallel algebra. Then, if we consider the invariant tensor and the connection 1 form in the Chern-Simons action, the general form, we obtain this relativistic Chern-Simons action, where we see the contributions of these extra fields to both vectors of the action along alpha 0 and alpha 1. So the non-relativistic counterpart of the algebra, of the teleparallel algebra enlarged with 2 U1 generators, can be derived considering an Innuno-Wigner contraction. For doing so, we shall first consider this decomposition of the capital A index in the following way. Then we have to introduce a dimensionless parameter psi, which will allow us to identify the relativistic generators in terms of the non-relativistic ones, which we have denoted with a tilde in this way. Besides, in order to ensure a finite non-relativistic symmetry after the contraction process, we have to consider the following scaling of the length parameter L in terms of the dimensionless parameter psi. Then, if we consider the previous identification and the limit of psi going to infinity in the commutation relations of the teleparallel algebra enlarged with 2 U1 generators, we obtain a non-relativistic symmetry spanned by the generators J, which are the spatial rotations. These are the Galilean boost. H are time translations. P are spatial translations. S and M are 2 central charges. And these generators satisfy the following commutators. We have denoted this algebra as a torsional non-relativistic algebra, which in the flat limit correspond to the extended Barman algebra. It is possible to show also that considering a particular redefinition of the generators, this torsional algebra can be written as two copies of the Napi-Witten algebra. Well, this torsional non-relativistic algebra admits this non-vanishing component of an invariant tensor, where we have also rescaled the relativistic parameters alpha 0 and alpha 1 in terms of this dimensionless parameter psi, in order to get to avoid infinities in the non-relativistic invariant tensor. Then the gauge connection, one form for the torsional non-relativistic algebra, is given by this expression, and the curvature or curvature form is given by this, where these are the components. Then the Chern-Simons action based on the torsional non-relativistic algebra is given by this expression. This is the most general action invariant under the torsional non-relativistic algebra and correspond to the non-relativistic version of the three-dimensional teleparallel Chern-Simons gravity. The term along alpha 0 tilde is indistinguishable from the exotic sector of the extending Barman gravity action, being the corresponding non-relativistic version of the exotic Lagrangian. The piece along alpha 1 tilde can be seen as a cosmological extension of the extending Barman gravity action, different to the one constructed with the extended Newton-Hooke symmetry. In this torsional non-relativistic gravity theory, then the cosmological constant can be seen as a source for the spatial torsion and for the curvature for the gauge field M. Indeed, on shell we find these two equations. And we can see that in the action, when we consider the flat limit, the theory reduces to the extended Barman gravity. Then this torsional non-relativistic gravity theory, as in the bosonic, as in the relativistic case, is characterized by a non-vanishing spatial torsion. We show that this non-relativistic gravity action can also be recovered directly from the relativistic U1 enlarged teleparallel Chern-Simons action. If we consider this, we can express the relativistic gauge fields in terms of the non-relativistic ones in this way. Then the non-relativistic action appears when we consider these expressions along with the rescaling of the parameters alpha 0 and alpha 1 on the relativistic Chern-Simons action, and then applying the limit of psi going to infinity. This is an alternative way to find the non-relativistic gravity action. We have also considered the supersymmetric extension of this non-relativistic teleparallel gravity. But the formulation of non-relativistic supergravity theories has only been approached recently and remains as a challenging task. One way to establish a well-defined non-relativistic limit when we have the presence of supersymmetry is considering the Lie algebra expansion method, which allow us to recover the respective non-relativistic version of a Lie superalgebra or superalgebra. In particular, as we will see, torsional non-relativistic superalgebra can be obtained by applying the so-called S-expansion method to the n equals 2 teleparallel super algebra. In few words, the S-expansion consists in combine the elements of a semigroup S with a structure constant of algebra or superalgebra, and the resulting algebra superalgebra is said to be an S-expanded superalgebra. And an advantage of working with the S-expansion is that it provides us with the non-vanishing component of an invariant tensor. So in this will be also the case. The S-expansion will provide us with the non-degenerate invariant tensor for the torsional non-relativistic superalgebra, and this we will be able to produce a well-defined torsional non-relativistic Chern-Simons Supergravity action. So the n equals 2 teleparallel superalgebra is spanned by the bosonic generators J and P, along with the generator set, and the fermionic charges Q. But in order to have a well-defined flat limit leading to the n equals 2 Poincare superalgebra extended with an SO2 orthomorphism algebra, we performed the following redefinition in order to introduce this generator S, which is the generator of the orthomorphism. Then the n equals 2 teleparallel superalgebra correspond to this, along with the commutators for the teleparallel algebra, which is a subalgebra of the superalgebra. We can see that, this n equals 2 teleparallel superalgebra admits the following non-vanishing components of non-degenerate invariant tensor. And we first proceed as before, considering the following decomposition of the A index, capital A index, in this way. And we have also to consider this redefinition of the supercharges in this way. Then we consider the following semigroup whose elements satisfy the following multiplication law. Here, lambda 3 is the zero element of the semigroup, such that the multiplication of this element for any other element of the semigroup is again the zero element of the semigroup. Well, before applying the S-expansion procedure, we have to consider the following subspace decomposition, B0 and B1. Here we see that we put the time component of the J and P generators in B0 and the spatial components in B1. And this decomposition satisfies this structure. We do the same with the semigroup. We consider this decomposition, which is said to be resonant since it satisfies the same structure as the subspaces, which is this structure. Well, after extracting a resonant subalgebra of the SE2 expansion of the n equals 2 teleparallel superalgebra and applying a 0S reduction, one get non-relativistic expanded superalgebra, which is spanned by this set of generators, which are related to the relativistic one through the semigroup elements in the following way. For example, J tilde is the lambda 0 multiplied by J0. For S tilde is lambda 2 multiplied by J0. I forgot to mention that the X expansion can be seen as a generalization of the non-linear procedure when the semigroup under consideration is, for example, this SE2, or when the semigroup belongs to the family which is SEN. This is a particular case when n is equal to 2. And these non-relativistic generators satisfy the torsional non-relativistic algebra that I showed you previously, along with the following commutation and anti-commutation relations involving the fermionic charges. We see that in the flat limit, this superalgebra leads to the extended Bellman superalgebra. Let us consider now the construction of the torsional non-relativistic supergravity action. For doing so, we first consider the gauge connection one form for this superalgebra, which is given by this expression, along with the component, the non-vanishing component of the invariant tensor. Then the non-relativistic supergravity action invariant under the torsional non-relativistic superalgebra is given by this expression. The non-relativistic Chern-Simons Supergravity action, as we see, contains two independent sectors and can be seen as a non-relativistic version of the n equals 2 teleparallel Chern-Simons supergravity action. The first term along alpha 0 tilde corresponds to a supersymmetric and non-relativistic exotic action, while the contribution along alpha 1 tilde can be seen as a supersymmetric cosmological extension of the extended Bellman gravity action. Here we can see that also when in the flat limit, this supergravity action leads to the most general extended Bellman supergravity action. And analogously to the bosonic case, the cosmological constant can be seen as a source for the spatial supertorsion and also for the curvature for the M gauge field. In particular, on Chern we have these two equations. Then again, this theory is characterized by a non-vanishing spatial supertorsion and also for the vanishing curvatures for the non-relativistic time and spatial component of the spin connection. I will use the last minute to show you how to introduce a non-vanishing torsion to the so-called Maxwell Chern-Simons gravity. During these last years, we have worked a lot with this, with the so-called Maxwell algebra, which is a particular extension and deformation of the Poincaré algebra, which is characterized by the non-vanishing commutator of the translational generator P, which is proportional to a new generator set, which is an abelian generator, and the gravity based on this symmetry describes as Poincaré a Riemannian and locally flat geometry. However, the presence of the additional gauge field along the set generator in the Maxwell case leads to new effects compared to GR. In particular, the gravitational Maxwell gauge field modifies not only the vacuum energy and angular momentum of the stationary configuration, but also the asymptotic structure. Indeed, in a work done in collaboration with Patrick Concha, Omar Valdivia, Nelson Merino, Patricio Salgado, and Olivera Miskovich, we showed that the asymptotic structure of the Maxwell gravity theory is correspond to the formation of the BMS3 algebra. Well, using the Chern-Simons formalism, we presented the three-dimensional gravity theory based on a particular deformation of the Maxwell algebra. This deformed Maxwell algebra is spanned by the generators J, P, and Z, which satisfy the following non-vanishing commutation relations. We have denoted this algebra as the form Maxwell algebra. We can see that when L goes to infinity, namely the flat limit, the deformed Maxwell algebra reduces to the Maxwell algebra. And also here we can see that when we set Z to 0, we recover the teleparallel algebra. Then this algebra can be seen or can be interpreted as a Maxwellian generalization of the teleparallel algebra. It is possible to show that considering this redefinition of the generators, the deformed Maxwell algebra can be written as one copy of the Lorentz algebra given by S, generated by S, and the Poincaré one, which is generated by L and T. But the motivation to use the basis J, P, and Z is twofold. First, we can recover the Maxwell Chern-Simons gravity theory in a particular limit, and also it reproduces the Maxwell field equations with non-vanishing torsion. Let us consider now the construction of the action invariant under this particular deformation of the Maxwell algebra. For this, we consider first the gauge connection. This is where this is the field line, this is the spin connection, and this is the new gauge field along the set generator. And the associated field strength can be written in this way. This is the usual Lorentz curvature. The hat is given again in terms of the usual torsion to form, and this is the curvature for the F gauge field. Here we can see that these first two curvatures are those for the teleparallel gravity. And when L goes to infinity, we recover the curvatures for the Maxwell gravity theory. The deformed Maxwell algebra admits the following non-degenerate invariant tensor, where alpha 0, alpha 1, and alpha 2 are arbitrary constants. And considering this invariant tensor and the connection 1 form in the general expression for the Chern-Simons action, we get this action, which is invariant under the deformed Maxwell algebra. We have three sectors along alpha 0, alpha 1, and alpha 2. We see that the first two terms along alpha 0 and alpha 1 are those for teleparallel gravity. And we see that when L goes to infinity or in the flat limit, this action reduces to the Maxwell Chern-Simons gravity action. When considering the condition on the arbitrary constant alpha 2 in order to get a non-degenerate invariant tensor, the equations of motion are given by the vanishing of the curvature to forms, these three equations. As we can see, the first two equations are those corresponding to the three-dimensional teleparallel gravity theory, in which the cosmological constant can be seen as a source for the torsion. And also, as I said before, in the flat limit, the field equations reduces to the field equations for the Maxwell gravity case. In particular, describing a flat geometry. And considering suitable boundary conditions, we found in a work done with Hamed Adami, Patrick Concha, and Hamid Safari that the asymptotic symmetry algebra for the Maxwell Chern-Simons gravity with torsion is given by this this algebra, which corresponds to an infinite dimensional lift of the deformed Maxwell algebra. And also we can see it has three charges, C1, C2, and C3. And the flat limit of this asymptotic symmetry algebra reduces to the deformed BMS3 algebra, being this the corresponding asymptotic symmetry of the Maxwell gravity theory in 3 dimensions. Well, now that we have seen how to include a non-vanishing torsion in a Chern-Simons gravity or supergravity theory, it could be interesting, for example, to study the appropriate boundary conditions to the teleparallel supergravity and analyze the boundary dynamics. It would be also interesting to investigate the Maxwellian version of the teleparallel supergravity. And we could also study the black hole solution and thermodynamics of the Maxwellian teleparallel gravity, which could bring information about the physical implications of having non-vanishing torsion in the Maxwell gravity theory. And thank you very much.
Okay, thank you so much, Evelyn, for this nice talk, this very interesting talk. And are there questions?
Actually, I have a question, or maybe 1 or 2.
Yes.
Probably I didn't get, but I didn't understand. I did not understand the role of these U1 factors. Then one has to add in order to be able to perform the non-relativistic limit. Why do you have to add these factors? Is there a physical meaning? Because, for example, if I think about quantum mechanics and I want to perform the classical limit, I do not have to add additional fields. So I would be interested in understanding why is that so in this case.
Well, these extra fields are crucial, as I said, in order to get a finite Lagrangian. And also, for example, in 3 dimensions, when we consider Poincaré, the non-relativistic limit is Galilei. When we consider an extra U1 generator, the non-relativistic limit is the Barman algebra. But neither Galilei nor the Barman algebra admit a non-degenerate invariant tensor. So that's why we add an extra U1 generator to obtain the a non-degenerate invariant tensor, which is crucial, which is a key ingredient in order to construct the action of the Lagrangian. That's all.
So it is not possible to perform the non-relativistic limit if you start by just Poincaré gravity. This is what I'm confused about. Okay.
you obtain for example, for Poincaré, you can construct an action, but
so you cannot redefine fields, for example, the metric or something, to be able to obtain a finite Lagrangian.
You are not able to obtain a curvature, or the vanishing of the curvature for every field.
Okay. Okay. Okay, thank you.
I see that there is also another question by Antonio.
Yeah, my question is the following. So I know that the Chern-Simons theory, it is very well known from a quantum field theory point of view because it is an integrable theory. So there are a lot of results regarding the path integral or observables like Wilson loops and other calculations. And I'm wondering how far it has been done, the same program with the Chern-Simons Supergravity or even gravity. I know for gravity there are works by Witten and other people where they compute some of the really path integral calculations. But has been done, this is also in the supergravity. Do you know some work where actually Chern-Simons Supergravity, it has been seriously taken into account from quantum field theory point of view?
Oh, no, I really don't know. I don't know if Professor Sanil is here or not. He knows.
Not really. The thing is that it's known that the quantum mechanical version of 2+1 gravity in the Chern-Simons formulation should exist, but I don't know of any serious calculation of that. In fact, there is a long discussion starting with Maloney and Witten in 2007, and then continue with Maloney and other collaborators for many years. And it's still not a settled question. What is the quantum theory of Chern-Simons gravity or supergravity?
Okay. Yeah, this is a quite interesting question. Yes.
Are there other questions?
Yeah, I have a question, Lucrezia.
Yes, please.
You talk about this teleparallel algebra or superalgebra, and it seems to me that this algebra is not necessarily restricted to the case of teleparallel gravity. And it's probably more adequate name is anti-de Sitter algebra or ESO, I don't know, whatever. Because the generators are exactly those of the anti-de Sitter algebra or superalgebra. And this is what Achukar Townsend discussed maybe 30 years ago or something. Isn't that right? Okay.
Is for me the question or for Evelyn? I didn't get it. Sorry, Hort.
But I understood that. But it was a question, and you were saying that the name should be another.
No, my comment was that essentially this algebra has been known for many years, and it was under the name of anti-de Sitter algebra or superalgebra, not under the name of teleparallel. I don't know why, whether there is a subtlety that something is different in this algebra, or there's something new about it. I don't know.
Isn't anti-de Sitter closing so that the two translations should be closing on Lorentz in anti-de Sitter case? Instead, if I don't remember, if I remember correctly, it closes on P. So it's not anti-de Sitter. It's different.
It's a different basis only. I think it's a change basis.
So you think if you change the basis, you just obtain the same. Because you say because
yes,
this
Isomorphic to
isomorphic, yes.
Yes, but what you get by considering, and in fact, I think that the point is that what is called teleparallel gravity is equivalent to general relativity, has been shown to be equivalent to general relativity. And here at the algebraic level that we have written this algebra in this way, we can see that it is isomorphic to anti-de Sitter. But at the dynamical level, I think that some subtleties arise already at the Chern-Simons level when you write the Chern-Simons formulation. Since in that case, you can see that the theory gives you a non-vanishing torsion, while and also at the non-relativistic level, in which case you get a non-vanishing spatial torsion, while in anti-de Sitter you would be expected to have a vanishing torsion or super torsion curvature. And this, I think, that could be also more evident in studying like McDowell-Mansouri gravity and supergravity. In higher dimensions, this could be more evident, I guess.
Well, my understanding was that if you take the anti-de Sitter group, or well, it's supersymmetric extensions, and study the Chern-Simons form for that, typically you get that the equations tell you that curvature is constant and torsion is constant. So this constant, either one could be zero or non-zero, but in general, that contains all of these options. But anyway, it's a matter of name, I suppose, more than mathematics, right?
But is this change of basis related to the fact that you have the 1 over L Filbine related instead of instead of on the curvature you have it on the torsion? So is this related to what you are saying right now, right?
Yes, and it's also related to the fact that you can always combine the spin connection and the Filbine with the epsilon symbol.
Yeah.
And you have freedom there to choose which one is which.
Okay. Yeah. So you could move the 1 over L epsilon to the curvature part instead of having it in the torsion. Okay.
Yes. Okay, so are there other questions? Okay, then if not, in any case, we can still discuss it in the discussion session. So thank you again, Evelyn, for the nice talk. And we can have a short break till 4:10, so an 8-minute break, and then we will meet again.
Okay, thank you very much.
Thank you.